Hello, my name is Aaron Jennings, and this is my presentation on our spectroscopy problem, Group M for University of New England, Organic Chemistry 1. Our problem here is carbon 10, hydrogen 12 with oxygen, and we are given the three graphs present, and I'm going to work through the next few slides breaking down what each peak means and trying to make sense of what the structure should end up being. Once we're given the formula for the compound, we can determine how saturated the bonds are with hydrogen, starting with the number of carbons multiplied by 2, adding 2, subtracting the number of hydrogens, and dividing by 2. Given 10 carbons, times 2 is 20, adding 2 is 22, subtracting the 12 hydrogens gives us 10, and dividing all that in half gives us 5. Leaving 5 bonds that are left unfulfilled with hydrogens. Given we're starting with 10 carbons, we can start with a ring to see how many we can fulfill after that, leaving us with 4 more carbons. And then trying to fill in the 5 left unsaturated, we can double up with inside the ring and add double bond to oxygen, possibly giving us a ketone. To determine what bonds are present, we are given this IR spectroscopy graph here for our compound. Below I added the key to show which peaks represent which types of bonds. So starting with our graph, furthest downfield is considered to the left with the higher numbers and upfield to the right with the lower numbers. Starting furthest downfield, we see our carbon-hydrogen single bond stretches right around the 3,000 mark, which is a good sign of an aromatic ring. Further upfield, we can see the carbon double bond to oxygen around the 1700 mark, which is a good sign of a ketone. And then more stretches at the 1500 mark that are carbon-carbon double bonds, which would also represent part of that aromatic ring. And then further upfield from there, right around the 1000, we can see carbon-carbon stretches, and those are single bonds. Another graph we are given to help determine the structure of the compound given is the chemical shifts one. Again, we are provided a key to show what types of bonds are present at what ranges. This graph will help determine the different types of carbon bonds, not the number of carbon bonds, but rather what other atoms they could potentially be bonded to. In this graph, we are given furthest downfield above the 210 mark. You're looking at a peak similar to the carbon double bonded to an oxygen ketone region. Then moving further upfield, we can see 4 distinct peaks that would represent a ring. Within the ring there are 6 carbons, but there are 4 different types of carbon bonds within the structure we have predicted. Further upfield from there are 2 distinct peaks, each representing a carbon-hydrogen single bond, each with 2 hydrogens. And then further upfield, the final peak is a carbon-hydrogen single bond representing a methyl group where it's carbon with 3 hydrogens. Add it all together gives us 8 distinct peaks for 8 different types of carbon bonds. The final graph we are given is the HNMR analysis for the hydrogen bond analysis. The top graph here is the one given for our compound. You can see 4 distinct peaks, each with peaks off to their sides. Down in the middle is the key we're given to show which functional groups could be in the peaks areas. The graph below shows the chemical shifts, the integration, the multiplicity, and the interpretation of which structure could be found along the way. As you can see, the higher end downfield around the 7.5, we see a sharp peak of the 5H. It's typically interpreted as an aromatic ring. Coming further upfield at the 3.5 mark or so, you can see a spike on the 2H. It's just a singlet there, and that's going to be a CH2 bond. Further up from there is another 2H. This one would be a quartet. As you can see, there's several peaks on each side of them, and that is also a CH2 bond. And on top there, you can see the 3H triplet, and that is representative of a methyl group or a carbon with 3 hydrogens attached to it. And after analyzing the graphs and their respective keys, where the peaks match up with which groups and which hydrogen bonds, I came up with benzyl acetone. It is 4-phenylbutan 2-one, and it looks something like this.